Hey physics friends, and welcome to 4.4, which I've entitled Putting It Into Practice. What we're going to be doing today is we're going to do 4 example problems where we're given a problem and we got to try to solve the answer. So these are going to have numbers associated with it, but we're all going to be doing the same idea that we've been talking about up to this point. We're going to draw a picture. So the steps to doing this. Draw a picture. Step 2, what are your knowns? And unknowns. You're going to put it into an equation. And doesn't make sense. So this is like chapter 3, where what do we know? What are we looking for? And then how do we get from A to B with equations? So underneath this drawing of a picture, it's really important that your picture has forces. Make sure that you label what the forces are, what directions they're going, and then their relative strength. To scale, meaning that if one force is the same as the other, I'm going to actually draw them as the same. Make sure that you label which direction is positive as well. I'm going to go through these and I'm going to follow these exact steps for all 4 of them just so you kind of have an idea of how to attack a problem like this. So number 67, it says you place a 7.5 kilogram television. So here's my TV and it's 7.50 kilograms. I'll always put the mass in black. It's not a force, it's a mass. You're putting it on a spring scale. So here's my scale. And it says the scale reads 78.4 newtons. So let's draw the forces that are acting on this. So right now, number 1, there's gravity. Number 2, there's a normal force. And these two things, since it's on a scale and it's not accelerating, the acceleration, and a lot of times I'll put acceleration in green. There's no acceleration right now. So that tells me that these two forces, this upward force and this downward force, those are equal and opposite. So they're telling me the force of gravity, or what they're telling me is the scale reads. The scale always reads the normal force, and that's a big idea. Not gravity. And that's kind of counterintuitive because imagine if you're sitting on a scale and then you're in an elevator and then somebody cuts the cable. Like that scale's not going to read anything as you're in free fall. And so that's going to be what the scale reads. It reads 0, even though you're still attracted to the earth. Like this. So this problem right here. Here's my picture. Here are my knowns and my unknowns, and it seems pretty straightforward. I almost didn't need to do that for this problem, but that's okay. What is the acceleration due to gravity at this location? So here's my picture. I have the forces, and they have relative strengths. They're the same size, which I'm going to make up positive. What are my knowns and what are my unknowns? My acceleration due to gravity is what this thing is looking for. I'm looking for the acceleration of gravity. There is an equation that relates force, acceleration of gravity, and mass all together. It's this. Now, when I'm trying to find the acceleration of gravity, I'm going to use the force of gravity to do that. And I do that quite a bit in this class. I change between mass and force by just multiplying by 9.8. So in this case, the force of gravity is 78.4. So here, those are my knowns and unknowns, and there's my equation I'm going to solve. My mass is 7.50. So my acceleration due to gravity, 78.4 divided by 7.5 comes out to be 10.5 meters per second squared. And I think I can use 3 significant figures, yes. Does it make sense? Yeah, usually the acceleration of gravity is right around 9.8, but this must be at a place that's very attractive, so it's accelerating more. So it seems like it's in the ballpark, right? It's normally 9.8, so yeah, totally makes sense. Let's try this again with a different problem, going through these exact steps. It says, assume that a scale is in an elevator on Earth. What would the force of the scale exert on a 53 kilogram person standing on it during the following situations? So let's draw our picture. So part A. Here you are. Constant speed. So that's important. I have my force of gravity. And because the acceleration, there is no acceleration, is 0, I also know that this normal force is going to be the same as gravity. So, since I am 53 kilograms, I can go over here. Force of gravity is equal to your mass times the acceleration of gravity. 53 times 9.8 is 520. So this force of gravity is equal to 520 newtons. And because I'm not accelerating, that also means that this is equal and opposite. So this is also 520 newtons. So part A says, what does the scale exert? What does the scale read? And remember from our last question that scales read the normal force, not gravity. So what's the normal force in this scenario? The scale is going to read 520. Part A. Part B, it's slowing down. So I'm going to take my same person, and I have gravity here as well. But this time, it says that it is slowing down while moving up. So if I'm moving this direction, but I'm slowing down, that means that my acceleration is in that direction. So I'm accelerating in the downward direction. And that tells me this. That tells me that this normal force has to be smaller than gravity. That's the only way I can accelerate in the downward amount. So, whoops. Just going to move this over here a little bit. Let's figure this out. So I'm going to go F equals ma. Wait, I do know gravity. It's the same 520 newtons. So when I go F equals ma, I'm going to use the net force. I'm going to use all the forces acting on my person. I've got a downward force. We should say which direction we want to be positive. I'm going to go up as positive. So I've got a negative 520 newtons. And I have a positive normal force. My mass is still 53 kilograms. And my acceleration, do they tell me what the acceleration is? Yeah, 2.0 meters per second squared. Now, we have to be careful. Since it's accelerating in this direction, that's the negative direction. So I have to make sure I put a negative there. Woo! So 53 times 2 is negative 106. And then that's a negative 520. So if I take negative 106 and I add 520 to it, I get a smaller number, and that's 410 with significant figures. And that checks out. That makes sense. It should be less than 520. That should be less than 520. So yeah, my scale reads 410 in this case. Part B. Part C, it's going to be speeding up while moving down. So, part C, have my same person here. I still have gravity. And they are accelerating, let's see, they're speeding up while moving down. So they're still going to be accelerating in this direction. So it wants to know, what does the scale read again? My guess is it's going to be the exact same thing. I have a sneaking suspicion that it's going to be 410. Let's just see if I'm correct. Because it's the same acceleration. So, yeah, I can totally tell right now it's going to be the same. So when I do this, F equals ma. It's the net force acting on it. I've got gravity, which is, you know what? In this problem, I'm going to switch this around. I'm going to make down positive. So watch this. So my gravity force is still 520. So I have a positive 520. And I have a negative normal force. My mass is still 53. And now my acceleration in this case is positive. It's a positive 2. So 53 times 2 is 106. And that's 520. Negative force normal. So I move that over so I get negative Fn. 106 minus 520 is negative 410. So that means that my normal force is negative times negative is a positive, 410 newtons. So that means that the force on the scale, which we expected, 410 newtons. Force on the scale is 410 newtons. Part C, D. It's moving down at a constant speed. So when you're moving down at a constant speed, that means that your acceleration is equal to 0. That means that this upward force is going to be the exact same as what your gravity is. And we know that gravity is 520 newtons. So that means that this is 520 newtons. So the force of the scale is equal to what the normal force reads, 520 newtons. And part E, last one. It slows to a stop while moving down. So, again, still have gravity. I'm slowing to a stop while moving down. So that means I'm accelerating in this direction. So that means that this scale is now, I know it's going to read bigger than 520. So when I use my F equals ma, again, the net force, it's all the forces acting on this. I'm going to say that up is positive. So I have a positive normal force, and I've got a negative gravity because gravity is pointing down and up was positive. My mass is 53. It doesn't matter. But my acceleration is positive. It's in the positive directions, and that is still... Oh, it doesn't say. Oh, man, that's lame. Sorry. That's not cool. A. I'm just going to use the letter A. So we can't really tell if they don't give us a number. So 53 times A is 53A. And then I'm going to add 520 to it. So what's the scale going to read? 520 plus 53A. Seems kind of silly. It'd be nice if it just gave me a number. But if they don't give you a number, just put a variable in there like they did there. So the scale is going to read 520 plus 53 times the acceleration. That was kind of a long one because there was like 5 parts to it. But again, I went through the same ideas. Draw my picture, show my forces, which way is positive, muy importante. Equations doesn't make sense. So let's try it again with number 3, which I labeled as 74. So there's a race car. I can tell that's the back. It's got a fin. It's got a mass of 710. It starts from rest. Ooh, so it starts out at rest. I'm going to do this in green, and then it accelerates. And it travels 40 meters, so this distance is 40 meters in 3 seconds. Okay, so I got a few things. I know that my initial velocity is 0 because it starts from rest. The distance is 40. The time is 3 seconds. What is the net force? So when this is all said and done, I want the net force is what I'm looking for. So here's my picture with the knowns. Now I'm going to put my forces in here. This car, there's gravity pulling down on it. If it's on the ground, there's a normal force that's equal and opposite because the car isn't floating off into space or it's not diving down towards the center of the earth. And it's accelerated. So this thing's getting faster. So something is pushing it forward. The engine. There isn't any mention of friction. There always is friction. We're going to totally ignore air resistance inside of physics in high school. So if they don't mention friction, you just ignore it. So in this problem, there is no friction. So there is no force this direction is what I'm saying. There is no force that one. So what we're going to do, we'll look for an equation that it relates all these things, and it's here. And the net force, gravity cancels off the normal because they're equal and opposite. So the net force is the engine force. That's the only one left over of all my forces. So the force of the engine is the net force. My mass is 710. And then shoot, I don't have the acceleration. So, man, if I had the acceleration, I could totally do this problem. So you know what I'm going to do? I'm going to take a side step. And I'm going to actually find the acceleration. I'm going to take all these things, find acceleration. And I think I can do that with this. To find my acceleration, initial velocity is 0, so 1/2. And then the time was 3 seconds. So 3 times 3 is 9. 9 divided by 2 is 4.5. And then 40 divided by 4.5. You get an acceleration of like 8.8 repeating. Now, you might think that I should round that to 8.9 because of 2 significant figures. Here's where I'm going to leave a few extra significant figures in here and then do my rounding at the very end. So if I take 710 and I multiply by 8.89, I get 6,300. And that's the net force. The net force is the force of the engine. So 6,300. There. Drew our picture with our forces. And then the pictures help out quite a bit. I had to take a sidestep in this one, finding the acceleration and then putting the acceleration into F equals ma. Last problem. Weather balloon. The instruments attached to a weather balloon have a mass of 5 kilograms. The balloon is released and it exerts an upward force of 98 newtons. So there's kind of a picture already drawn here, so I'm just going to add to it. We'll call this is actually called the buoyant force, F sub B. You can call it force up, whatever, a force of balloon. But this buoyant force is 98 newtons. It's what makes things float on top of anything else, a buoyant force. This thing weighs has a mass of 5 kilograms, so my force of gravity, remember, if this thing has a mass of 5 kilograms, and we multiply by 9.8, 5 times 9.8 is 49 newtons. So this thing has a weight of 49 newtons. We can see from this picture right here, this is totally going to accelerate this direction because the upward force is much bigger than the downward force. In fact, it's twice as big. Now, part A says, what is the acceleration? So we look for an equation. Oh boy, we better declare which direction is positive. So I'm going to make up positive through all of this stuff. So my net force is all the forces acting on this thing. A positive 98 and a negative 49. My mass is 5. And my acceleration. So 98 minus 49, 49 divided by 5. The acceleration comes out to, this is funny, 9.8 meters per second squared. This thing is accelerating upwards at 1 g. It's accelerating away from the Earth at exactly 1 g. Part B. It says after the balloon has accelerated for 10 seconds, the instruments are released. What's the velocity? Woo! How fast is it going? I'm assuming they release it from rest. The acceleration is a positive 9.8 and for 10 seconds. So you can see we're maybe going to plug it into one of these equations. Vf equals Vi plus At. Final velocity unknown. Initial velocity is 0. 9.8 times 10 is 98. So how fast is it going? 98 meters per second in that direction away from Earth. Part C. What is the net force acting on the instruments after their release? So my instruments here, they had a force of balloon, the buoyancy of 98 newtons, and then it was also gravity pulling down on it, and that was 49 newtons. The moment the balloon pops, this goes away. So what's the net force acting on this? The net force is gravity acting on it, and it's 49 newtons towards Earth. There's no more upward force on it. That's the total net force acting on this thing. And then part D says, when does the direction of the instrument's velocity first becomes downward? So this thing, what's happening is, it's at the very beginning, as soon as the balloon pops, we found out that it was moving 98 meters per second. That's what we found out in this part right here. So it's going up and it's slowing down, and then it comes to a stop. So I'm still going to treat up as positive, but my initial velocity is 98 meters per second, positive, and then it comes to, at the very top, it comes to rest. The acceleration, it's accelerating in this direction under gravity, and that's the negative direction, right? Because this way is positive and gravity is pulling you down, so the acceleration is negative 9.8. And it wants to know when. How long does that take? So we'll do this again. Choose my equation. From what are my knowns? What are my unknowns? There's an equation that relates them all. So, wait, we don't know the time. Time is unknown. So bring this over, and that also becomes 10 seconds. So it takes 10 seconds to reach the top of its peak. Boy, these are pretty nice numbers. They all kind of 98, 10, and 10. All right, friends. Thanks for paying attention. Here's quite a few examples. And it took me a long time because I'm really making sure I want to draw a picture, show your forces. Is one bigger than the other? And the most important thing is which forces are there. So good luck.